let us now turn to task 2. In this task we consider the following Dirichlet problem, which is on the strong formulation of it takes this form, and on the boundary u is equal to 0. The set omega is for simplicity just from 0 to 1 square, so it's this unit square in fact. In this we have this partial differential equation a little bit different from the harmonic equation, the Laplace equation, but you can see it's some variant of the Poisson equation. In this task we are asked to verify that we have the corresponding weak formulation of this problem takes the following form. We find u element in the Sobolev space W0 such that A of u v is equal to L of v for all v element in this Sobolev space, where the bilinear form u A of u v is defined by this integral, and the linear form L of v is given by this integral. We also got the hint to use that 4 times the partial derivative of u with respect to x1 plus 2 times the second derivative of u with respect to x2 in fact is equal to the divergence of this vector. This hint is not always present in exam tasks, so you should be able to replace the second derivative terms on the left side here with some divergence of a vector. This is very essential for using the Green's formula in the task. We are in the solution of this task, we use the Green's formula. First we multiply the equation, the strong formulation of the equation, with some general test function v in the Sobolev space W0 on both sides of the equation. This is very usual. And after having done this, we integrate over the set omega on both sides. So now we use the Green's formula, which takes this form. The integral of this term is equal to the sum of these two integrals. So if we replace now w, which is always a vector, by this vector, and of course we have to we don't have v here, so we have to replace this phi with v, and then we obtain the following. Let me just show you. So here we have changed this, replaced v w and phi with this and with v. So what we now can see is that in this we realize that this term is, you see, on the right hand side, the left hand side of the equation we obtained by multiplying with v and integrating is now identical with the left side of the Green's formula. So now we can replace the right hand side of the Green's formula with this, and so that we have done here. And now we do the following observation. Since we are using only test functions v in W0, we note that v is 0 on the boundary and this is a boundary integral, so here we can put in the integral v equal to 0 all over this this boundary. Therefore, this integral will vanish. So therefore, we obtain this identity. This guy is equal to this guy. And if we now multiply with minus 1 on both sides, we obtain that this without minus is equal to this without minus. And this is exactly what we were going to prove, because this is in fact the bilinear form A of u v, and this is the linear form L of v. Next, we are asked to list very shortly the steps we have to verify in order to prove that there exists a unique solution of the weak formulation, which we called 0.1. Way of doing this is just to observe that A of uv is a bilinear form, that L is a linear form, and next check that the conditions 2 to 4 are satisfied. That means that we should check that A is continuous and V elliptic, and that the linear form is continuous on W0. The existence and uniqueness of the solution of the weak formulation follows then by the Lux-Milgram lemma. So in part C, we are asked to formulate the minimum problem corresponding to this weak formulation. And we are also asked to explain why this minimum problem is equivalent with this weak formulation. To formulate the minimum problem is just doing this. The minimum formulation is just to find u in this W0 such that this is obtained. That is the same as putting f of u less or equal to f of phi for every phi element in the sublet space, W0. And here we always have that this energy functional f of phi is half of a of phi phi minus L of phi, as we have learned in the lectures. So putting in the bilinear form v equal to phi and u equal to phi into this into the expression, then we obtain this directly. The reason why the minimum formulation and the weak formulation are equivalent follows by the theorem which stated, we showed you in the lecture, that there exists a theorem stating that if the conditions 1 to 4 are satisfied, then these two formulations are equivalent. We have already discussed the items 2 to 4. 1 just simply means that A is symmetric. So we have to prove that A is symmetric, and it is symmetric. It's easy to see. Next, we will